All right. Good morning, everyone. Sorry for the little this morning with the room door. How's everyone doing after the with the lab exercises from the last week? Okay. Yeah. Okay. Good. We'll have a chance to discuss them a bit later. But for now, for session 3, we're going to move into hypothesis testing. Oops, wait a minute. This is not quite the final version. Okay, so I'm going to introduce hypothesis testing today, along with type 1 and type 2 error and power analysis, as well as confidence intervals. And we're continuing today in chapter 1 of the book, but I added an extra optional reading for you today because I found that this section of the book really, it goes right into some examples, but that has very little on kind of background and conceptual things about hypothesis testing, which are important. So this is another free online textbook that I've used in other courses and has a little bit more sort of description of hypothesis testing, which you might find useful. And it's free anyways, so it's a good reference to have around. So just to review what hopefully you've learned from last week, a big one was identifying the difference between populations and samplings, and populations and samples, as well as the difference between population distributions and sampling distributions. You should be able to give several sampling strategies that can be used. Identify properties of the normal distribution, which will come up again today, and also define the central limit theorem and its 3 parts and give some examples of its application. So just to review this bit about population and sampling distributions, because it's key to everything that we're doing today. Remember that population distributions, each point or realization from that distribution represents an individual, whereas with sampling distributions, every realization or point is a sample, resulting in a sampling statistic, and it's a distribution of those sampling statistics. That distribution depends not only on properties of the population, but it also depends on the sample size. And for large distributions, or for large samples, the sampling distribution is known from the central limit theorem. All right, hypothesis testing. Why do we do it? We do hypothesis testing when we want to make yes or no statements, such as whether a population mean has a hypothesized value, or for example, an intervention causes a measurable effect relative to a control group. So it's things where we want to not necessarily say something about magnitude, but we just want to say yes or no to a hypothesis such as these. Usually expressed between 2 populations, or do hypertensive smoking men have the same mean cholesterol as the general population? Just to give a couple of examples. These are both things that you would answer with a yes or no. Should note that it's not the only framework for inferential statistics. It's maybe the one you will see the most, but there are also confidence intervals, which we'll talk about a fair bit today, and which I tend to promote even over hypothesis testing, because they provide not only an indication of whether your sample is consistent with a null hypothesis, but also gives you a range of plausible intervals for the actual value that you might be interested in, such as how much a gene is differentially expressed, or how different the cholesterol level is between two populations. Posterior probabilities Bayesian statistics have an entirely different take on how they use probability in inferential statistics, something that I don't do a whole lot of, but is an alternative way of approaching inference. I don't know if any of you had a chance to read it yet, but this is an interesting and short read from Nature. P-values are just the tip of the iceberg, and it's a nice short commentary on some of the controversies that that exist in the literature and scientific community around the use of p-values and null hypothesis significance testing. So the logic of what we're doing in hypothesis testing, it's basically the same regardless of what kind of test we're doing. Here's a couple examples. With a one sample test, we take this sample and assume that it comes from one of two population distributions, either usual one, which we've seen in the past, or which is true for without any intervention, that is from a population that is known, versus a potentially new distribution that is there due to an intervention or some change in condition. And then with two samples, instead of one, we draw two samples, and they either come from a single population or from two different populations. And these correspond to our null and alternative hypotheses in these two examples. The sort of classic example of the logic of hypothesis testing is you've drawn some beans from a bag. You see that only a few of those beans are white, but in the bag, most of them are white. So probably this handful of beans came from somewhere else, because you'd be unlikely to reach into this bag with only a few white beans, or that's mostly white beans, and draw all black beans. And the classic two sample inference would be you have two handfuls, and one of them, most of the beans are white, and another one, most are black. So you're unlikely to have drawn those from the same bag. Not impossible, because if it's a random sample, there's always a chance that you just happened to get a cluster of white or black beans. But this is what inference is about. We would infer that it is unlikely in these situations. You are typically going to perform hypothesis testing with a line of code, probably, but that glosses over a lot of steps that are involved in formal hypothesis testing. The first step of hypothesis testing is stating your hypothesis, and this is something that is usually done before the experiment is done, before you do any analysis, anything. This is your setup for doing anything, and it's a little bit different from hypotheses as we often state them for, say, for a grant proposal or in a paper. You will often state your hypothesis in terms of some new thing that you believe is true. I believe that this drug will lower cholesterol in a population of hypertensive smoking males. So that would be a hypothesis that you might state, but for the logic of hypothesis testing, it's put somewhat more formally than that in terms of the null and alternative hypotheses, and I'll give you examples of these in a bit, and they're written down usually with equations. You specify your significance level, alpha 0.05 being the most popular value, but it can be anything. At this point, you perform your experiment, draw your sample size of n, and compute your test statistic, which in the case of testing sample means will be your z or your t statistic. And we will use a normal distribution if we're taking advantage of the central limit theorem, or a t-distribution when you have to estimate your, if you have to estimate the standard deviation from the sample. From this, you determine your p-value, which is based on this distribution. It's the probability from the test statistic you observed out to the furthest tail of the distribution and multiplied by 2 for a two-tailed test. And that's your p-value, the probability of observing the test statistic that you have or something more extreme given your null distribution as assumed under the null hypothesis. Then finally, you compare the p-value to your significance level alpha and either reject or do not reject your null hypothesis and state conclusions in terms of your subject matter. So these details are for a one sample ZRT test. And for other tests, the calculation of the test statistic will be different. Everything else is the same. So even if you don't go through the steps of writing these all out and numbering them, it's good to know that these are the steps. If you are performing hypothesis testing, you implicitly are going through these steps as you perform and interpret your test. So in frequentist statistics, there's this idea of the true state of nature. That is the assumption that there is some truth that we can't observe directly and we can only make inference about through limited samples. And by comparison of that to the result of our test, we get our definitions of types of errors or correct inference and power. So looking at this first row where the null hypothesis is true, so that's the state of nature where we're testing an ineffective drug, we're studying a gene that is not differentially expressed. That's the true state of nature. If we, however, reject H0 due to sampling variability, so we just happen to get that handful of white beans from the bag that contains mostly black beans, that's type 1 error that we controlled to be less than alpha through our statistical hypothesis tests. If we fail to reject H0, then that's the correct decision in this situation, failing to reject H0 when H0 is true. Now, if H0 is false, or in other words, the alternative hypothesis is true, so the drug is effective, the gene is differentially expressed, that's, and we correctly reject H0, that's of course no error. The alternative is true, and we reject the null hypothesis. And the probability of doing that is what we call the power. It's your power to correctly reject a false null hypothesis. You'll find there's often a little bit of awkward language around hypothesis testing where we talk about rejecting the null hypothesis or failing to reject the null hypothesis, because we usually avoid language like accepting the null hypothesis. We only find evidence against the null hypothesis. And finally, if H0 is false, but we fail to reject it, that is a type 2 error. So we should have found that the drug was effective, but we did not. That's a type 2 error. Or a false negative, and we use beta to write down that probability. So these are probably the three most, we've learned some key vocabulary already today. The null and alternative hypotheses, type 1 error, type 2 error, and power. Any questions about these so far? So just to make it maybe a little bit more concrete with a plot, under a two-sided hypothesis test, we assume that that if the null hypothesis is true, then let's say the cholesterol level is the same as the national average, it's 150, something like that. And due to sampling variation, we might get a sample with larger or smaller mean. In this case, the null hypothesis is written as follows so this is a two-sided one sample test. It's one sample because we're talking about the mean of a single sample, and the null hypothesis is that it's equal to a hypothesized population mean. And then the alternative hypothesis is that the mean from our target population is different from the mean of the population, of our null population. So we frame the hypothesis test in terms of a null sampling distribution. And if our test statistic is the T and Z are calculated in the same way, it's your sample mean minus the mean under the null distribution divided by the standard deviation. And under the null distribution, that's going to be normally distributed with mean 0 and standard deviation 1. So if we take our sample, calculate that Z or T, and find that it's out here in one of these rejection regions, then we're going to reject the null hypothesis. So I have a question. Actually, let's first, I want to mention to you the one-sided test, which is only used in very special situations. Here, the null hypothesis is that our mean is greater than or equal to the mean under the null, or it could be the other direction, noting that H0 always includes the no difference. So there's an inequality, but the equals part of it is included under the null distribution. And then the alternative hypothesis includes everything else. So in this case, that the means are less than the null. So this is somewhat different because we're only going to count the area under one tail, because everywhere to the left, this is part of the null distribution. And as a result, you can get a p-value that's half as big as in the two-sided test. So here's my question for you. Our hypothesis is that this drug is effective at reducing cholesterol in hypertensive smoking males. Would we set this up as a one-sided or a two-sided hypothesis test? When our research hypothesis is that this drug reduces cholesterol in a population of hypertensive smoking males? One-sided or two-sided test?
If it reduces,
Mm-hmm.
so one-sided.
Why do you say one-sided?
Because if you have said if it changes, decrease or increase,
Mm-hmm.
then I would say two-sided.
Time sharing it if you did the one-sided test. The reason is that we perform the hypothesis test under the assumption that the null hypothesis is true, not our research hypothesis. So what is the null hypothesis or what is the null hypothesis if the drug is ineffective, if it's just a placebo?
The drug is
What the null hypothesis. So what would the null hypothesis be? What do we expect in our treated population if the drug is ineffective? That's right. So what is that? That's a two-sided test, that the means are equal. And you would expect to get samples with means higher and lower than that control mean. So that's a two-sided test. This is a very common misunderstanding. You have to think about, what do you expect under the null hypothesis? So, and in this case, we don't expect under the null hypothesis for the drug to be harmful. I mean, this is what I mean. It's only under very special circumstances that you would use a one-sided test. The one example in clinical trials where they are used is in so-called equivalency tests for a drug that you actually expect it, or your research hypothesis is that it's equivalent to an existing standard of care. And so your alternative, your alternative hypothesis in this case, or let's see, and it's always a little bit confusing for me to think about, but under your null hypothesis, where the drug is where you're going to fail the test and decide not to use the drug is only when it is worse, and under if you're going to use the drug if it is the same or better. So you might set that up as a one-sided alternative. So you would have equal or better under your null hypothesis and only worse under your alternative. These are rare situations. So as a general rule, you're going to use a two-sided test.
But the null hypothesis also in the case of the drugs seems to be the drug A is equally effective as drug B. So
yeah, you would set it up that way only if you wanted your type 1 error and your rejection to happen in the case where your alternative drug is worse. And in the case of no evidence, you would assume equivalency or better. I have in practice never used a one-sided test, so As a side note, there are certain tests that we'll get to next week that are inherently one-tailed tests, such as the chi-squared test, such as the ANOVA F test, where you will only look at one tail, but that's because it's inherently a one-tailed distribution, and any sort of departure results in more extreme. Any departure from the mean results in larger positive test statistics. So it's not the same thing here, because we can have positive or negative extreme values. And just to add to the possibilities here, there is also the paired test. So in the one sample test, we draw a single sample, compare its mean to a theoretical mean under the null distribution. In the two sample test, we compare the means of the populations from which the two samples were drawn. And then in the paired test, it's a single sample, but we calculate differences between paired observations. Some examples would be weights before and after a treatment, any sort of a difference between twins, anything where you have a naturally paired measurement. And these can be very good, very efficient designs in terms of using fewer samples and reducing the individual to individual sampling variation. For the example, weights is a good example, because in your population you might have people who vary a lot by weight, but the change in weight before and after treatment may be less variable than the variation of weights in the population. And in this case, it is incorrect to treat these as independent samples, because the weight before and after of an individual is not independent. It's a paired measurement. I'm going to go through a few of the common abuses of the p-value. It's helpful just to keep in mind what exactly the p-value is as you're interpreting them. And that is, it's your probability of observing a sample as or more extreme as what you've observed. So in your two-sided test statistic, it's the probability of observing a test statistic with greater magnitude than the one you observed, assuming that H0 is true. So under hypothesis testing, you're always acting under the assumption that the null hypothesis is true. It's a random variable, so don't treat it as precise. I don't like to see p equals 3.2974 times 10 to the minus 4, because the extra digits just don't mean anything. It's not a precise measurement. It is subject to sampling variation. Getting too creative with what you do with p-values, such as interpreting differences or ratios between p-values. I saw a poster once that was comparing two different methods, and found that with one, they got a p-value of 0.02, and with another one, a p-value of 0.025, and so concluded that the one where they got the p-value of 0.02 is better. And in that example, with fairly close p-values, you might as well flip a coin and to decide which method is better. Those sorts of small differences between p-values really aren't meaningful. Don't lose track of the test assumptions, and in particular, independence of observations. P-values are, no matter what test you're doing, there's going to be some assumption that this is a random sample of independent observations. And if that assumption is untrue, if There are situations that are called pseudo-replication, where you have observations that look independent but aren't truly, such as anything where you have correlated measurements, such as a bunch of measurements of the weight of one person versus a bunch of measurements of the weight of another person. Those are not independent measurements. You could repeat that weighing a bunch of times and get a very small p-value, but you would have to think carefully about what that p-value actually means. One thing I do recommend when you are doing multiple testing, such as performing hundreds or thousands of hypothesis tests, is to use some fairly moderate p-value cutoff and then use something else, an effect size like amount of differential expression for doing the actual ranking. Keep in mind that in particular, very small p-values, they vary a lot under repeated sampling. The smaller your p-value is, the more extreme the variations you'll have just by drawing another sample. And additionally, small p-values are correspond to probabilities far away in the tails of your sampling distribution, and so they become even more sensitive to assumptions about your sampling distribution. So that difference between a normal distribution and a t distribution is pretty small. If you're talking around p equals 0.05, your p-values will be very similar depending on which of those distributions you use. But if you're talking about p-values out at 0.0001, they'll be very different depending on which sampling distribution you're assuming. So small p-values are especially sensitive both to sampling and to test assumptions.
So you said that the value is a random variable because it depends on the sampling.
That's right. You can draw repeated samples using from the same population using the exact same methods, and you'll get different p-values every time. Something to think about, right?
Oh, yes, because you usually tend to think that the p-value is given in certain. You don't think that it's a random variable.
No.
So.
Yeah, I think that even more generally than that, it's easy to lose track of the fact that the data that you have are just one possible sample out of an infinite number of samples you might have drawn from a population. So everything that you observe is just a sample. It's an incomplete picture of your population, and it's subject to random variability. So when you calculate a mean, anything you calculate from it is a random variable.
Yes.
And I feel like one aspect of developing your statistical intuition is just starting to have an intuition of how variable all of the different things that you do from a sample are. So, you know, when you make a plot, calculate some statistic from it, just having an understanding of how variable those would be if you were to repeat your sample, and just having a sense for which things are reliable and which ones are not. And hypothesis testing is really only a guide to that. It's not the only aspect of it. you can imagine all of the various plots that you make from your data, all of those have a random component to them. Some of them will be more random than others. So if we fail to reject H0, is the probability that H0 is true equal to 1 minus alpha? Yes or no? No. I just didn't want you to spend any time thinking that maybe the answer was yes. It's no. The probability that H0 is true is not determinable from alpha alone. Or put another way, no evidence of a difference is not evidence of no difference. So keep in mind that you always start with the assumption that the null hypothesis is true. And one way you could fail to reject your null hypothesis would be by not collecting any data. So then you have, well, I don't know what your p-value is in that case, but you've failed to reject the null hypothesis without collecting any evidence in favor of it either. Secondly, statistical significance does not necessarily mean practical significance. Our hypothesis tests that we have talked about so far are inferences about the mean. So we reject the null hypothesis if we find that the difference in means that we observe is unlikely to have occurred under the null hypothesis. Now, as if you collect a relatively large sample size, you can detect very small differences in means. So you might have a drug that you have good evidence of its effectiveness, but it reduces cholesterol by 0.5 point, which would not be clinically significant. And of course, it's worth keeping in mind also that your hypothesis test has to do in the case of a small p-value for a very slightly effective drug, you might have still almost a complete overlap in your two populations. So you might have almost half of, maybe 49% of your treated population having a higher cholesterol than people in your untreated population. So it's just the means that are different. It doesn't say anything about the fraction of individuals that have a larger or smaller weight or cholesterol level or whatever. Finally, keep in mind that choice of alpha equals 0.05. It's very popular, but it is arbitrary. So one result where you have a p-value of 0.055 is actually really essentially the same as another result with a p-value of 0.04. The importance of the 0.05 is only when you are setting out before undertaking your study to say that I'm only going to have a 1 in 20 chance of committing a type 1 error. And if you accept p-values above your alpha, that probability will be correspondingly higher. But that cutoff is really arbitrary. So, so for this reason, in the example, if you have two primary endpoints, such as overall survival and recurrence for cancer, and you're doing a test for a treatment and get a p-value of 0.055 for overall survival and 0.04 for recurrence, it's not it's not a basis on which to compare those two endpoints and say that the drug is effective for reducing recurrence but not for survival. I wouldn't say that. Okay, power. So once again, we do hypothesis testing under the assumption that the null hypothesis is true. Power analysis is different because we do it under the assumption that the null hypothesis is false, or equivalently that an alternative hypothesis is true. And another difference is that whereas we perform our hypothesis test based on our sample after collecting the data, its inference about our sample, we do power analysis during the study design before we collect data. To answer questions such as as we hypothesize, what's going to be the probability of rejecting the null given our study design? Or alternatively, if the alternative hypothesis is true as we think, what sample size do we need to have a 90% probability of rejecting the null hypothesis? And I find visual demos really helpful for understanding power. This is a Shiny app that I'll demo right now. There's also a nice one within R in the teaching demos package. I'm going to open up the Shiny app. Okay, so we have a plot of two distributions here. There is the alternative hypothesis that we're going to assume is true, and then there's the null hypothesis, which is the one that we're going to use when we perform our hypothesis test in the future. So how do we do a power calculation? The alternative and the null hypothesis, the sampling distributions, of course, have to be different. And so let's assume that, that the null hypothesis is true. This is going to be this curve on the right, the distribution of sample statistics that we will observe over repeated sampling. It's centered right over here. When we perform the null hypothesis significance test, it will be under the assumption that our test statistic is somewhere else under the null, and we will reject H0 if we get a value of the sample statistic somewhere out in the tails. So what is the probability of rejecting H0? We just look in this region in the tails, and so this we can calculate for it, like where is this under, if we're talking about a normal sampling distribution, this would be, for any distribution, this would be the 97.5th quantile or percentile. If we're doing a alpha equals 0.05, this would be 1.96, a value of the z-statistic of 1.96. Then our power analysis is the probability of getting a z-statistic more extreme than 1.96, assuming that the alternative hypothesis is true. So does this logic make sense? We've assumed that this alternative hypothesis is true, and we're calculating the probability under this alternative sampling distribution of getting a test statistic in our rejection region for the hypothesis test. So the only thing that we use in the power calculation from the null hypothesis is this critical value where the rejection is going to occur. And then we use our hypothesized alternative to calculate the probability of getting a test statistic in that rejection region. So what's going to happen if I take alpha from 0.05 down to 0.01? What's going to happen in this plot? Anyone? Tell me how this plot is going to change as I move alpha from 0.05 down to 0.01. So I want to reduce my type 1 error rate in this planned hypothesis test.
The rejection region of H0 becomes smaller.
Yep, the rejection region becomes smaller. So what happens to this line here? It's going to move over to the right, right? And this one will move over to the left. So what happens is this line moves over to the right. What happens to this shaded area of the power? It'll reduce the power. Let's watch that happen. Yeah, so now the power went down to 0.045. It was at 0.6 or something like that. So this makes sense, right? If you want to be extremely confident that you will not reject the null when the null is true, it also makes it more likely that you're going to fail to reject the null when the null is false. If we move this the other way, so we're going to be permissive about type 1 error, say it's not such a big deal if we reject the null when the null is true. It makes these rejection regions of the hypothesis test larger. It increases the power. Regardless of what distribution, what test you're doing, that relationship always holds. That when you increase alpha, you increase your power. Okay, so now what about this difference in means? So this is really hypothesized. We don't know what the true difference in means is, but we have to assume some true alternative hypothesis in order to do a power analysis. People will often do this based on what difference would be clinically significant or biologically significant. So it's just based on how big of a difference would be of interest. And it's sometimes based on a pilot study. So you undertake your power analysis saying, if there's a true difference in means of 0.5 kilograms, 0.5 whatever, I want to be able to see it. So what's going to happen here if I increase this difference in the means? What's going to happen to these plots? What'll happen to H0? H0 and the shading. The shading of the rejection regions.
I guess it's still going to stay the same. The shade is going to strike to the right.
That's
So
right.
we will have a less overlap region, and I guess that power will be more.
Yep, so H0 is going to stay exactly the same. This is the difference, the alternative hypothesis that we're changing. So the H0 and the shaded regions will stay the same. this whole distribution under the alternative hypothesis is going to move to the right. And the power is going to increase. So let's just check that out. I moved it quite a bit. It's off the screen. Let's move it back a little bit. We have pretty high power now. I'll bring alpha back down to 0.05. Okay. Now, how about what's going to happen if we increase the sample size in each group? Well, first, what'll happen to the null sampling distribution? We're using the central limit theorem here. It'll become narrower, right? Because what's the standard deviation of this sampling distribution? What's it called? There's a name for the standard deviation of a normal sampling distribution. Sigma is what we used for the standard deviation of the population. But for the sampling distribution, and S is our estimate of the population standard deviation, but estimated from a sample. So, but that's the variability of individuals in the sample. How about the variability of the sampling distribution itself? That's the standard error.
Always use this. Synonymous.
What do you use as synonymous?
Standard deviation and standard error.
Many people do, but you shouldn't. Standard deviation refers to individuals, variability of individuals, and standard error refers specifically to the variability of means in a sampling distribution. So I did say here that the standard deviation of the sampling distribution is called the standard error. So, standard deviation is a very general term to mean, one of the two parameters of a normal distribution. But standard error has a very specific meaning.
What should I use then for the data that arrives into my lab, for example? Those are us.
Tell me more specifically.
Okay, of course I don't have the entire population, I have a sample.
Yeah.
So I'm always
sample of what?
Sample of patients having cancers.
Okay, you have a sample of patients having cancer. What are you measuring?
So I have a sample of patients having cancer and a sample of patients doesn't have cancer, and I measure the gene expression of the two samples.
Okay.
Okay, so that's the standard error. If I compute the variation from the mean, that's the standard error.
So
because it's a sample, so I will always work with standard error.
No. So if you calculate, let's just take one gene as an example. You calculate the mean and standard deviation of all of the observations in your sample. That is the standard deviation of your gene expression observations. Now, if you divide that by the square root of n, that is the standard error. Or maybe a better term to use for it would be the standard error. They're going to be very different, and they have very different interpretations. Yeah. So the standard error of the mean tells you about the variability of means if you were to do additional samples, whereas the standard deviation tells you about the variability of gene expression in individuals.
Okay, so in a perfect world where I can screen the old people in the Earth, I will end up having 0 standard error.
That's right. You have no uncertainty in the mean anymore. Yeah.
Okay.
Yeah, you have
Well,
0.
I will keep that, but I will still have standard deviation.
Exactly. The variability of individuals will remain as you sample everyone in the world, but your variability in the mean is gone then. So that's the difference between standard deviation of individuals and the standard error. And I've heard, I've been asked several times, like, should I report when I, put error bars, or I put a plus or minus, should I use standard error or standard deviation? And my answer is just, they're totally different. What do you want to describe? Do you want to describe your uncertainty in the mean? Although standard error isn't exactly uncertainty in the mean. Or do you want to describe the variability of individuals?
Okay, well, most of the time, in type of experience, so we try to understand the variation of the gene itself. We don't actually care about how much is difference from the mean according to the sample size, since we can actually have power to change that. I can't tell to the hospital to sequence more and more and more and more. They have the samples, they will give them data, and that's it.
You will care about the variability in the mean when you want to compare 2 samples. You will probably compare the means of those 2 samples.
If I have 2 studies from 2 different hospitals, then I can say that my results are these ones and have this standard error from the mean, and the other data set of the same disease as that other standard error. That might be significant information to give. Is this picture correct?
Almost. So I think that if you had 2 samples taken from different hospitals, maybe where treatment is different or something like that, what you would most likely be interested in your in a hypothesis test are the means. Is there a difference in those means? And your significance test would be on the difference. And if you built a confidence interval, it would be on the difference itself, not actually creating one, calculating one standard error for your sample from hospital A and another standard error from hospital B. You would take all of the data and calculate a confidence interval for the difference and a hypothesis test on the difference in the 2. So I feel like it's very easy to feel like you understand the difference between these individual distributions of individuals and the sampling distributions, and then get confused about it again. So so please continue asking questions about that if you're at all unsure. But if there's one thing I hope you've learned so far, it would be what is that difference between a standard deviation of individuals and a standard error, and being able to think about which one you want to report for your study. You report that standard deviation variable individuals, or you would report the standard error, or more likely a confidence interval, which we'll get to if you wanted to provide a confidence interval on the mean.
Another thing I wanted to make to the information you gave previously with this one. We said that if we take a population of 500 samples, since the population size is not related with the sample size is not related with the population size, actually. If I take from 500 above, I can can state that I have a good sample size to do my calculations on.
Mhm.
So how? But still, I will have a standard error there
Mhm.
because it's related to the 500.
Yep.
So standard error in this picture seems to be way less important as information. Since I can stop at 500 to have a reasonable amount of points to draw my distribution, I will keep having a standard error, but I don't care because I have enough points to actually do my research and make calculations on. Because I have enough points for drawing my distribution and then say what I want to say.
Because you have enough points for drawing your distribution.
I mean, if I didn't get everything, so this part wrong, previously we said that from 500 above, I have enough point for drawing my distribution of the phenomenon that I'm going to investigate.
Or I think what we said was that the central limit theorem holds quite strongly for sample sizes of 500 and above. So the those all three components of the central limit theorem will be true regardless of the population distribution.
So but I can take this statement in my mind and save it as, if I have 500 points, I'm like pretty much sure that what I'm doing is what I'm seeing is the real thing that I'm seeing if I have no selection bias.
It's not so much that what you're seeing is the real thing. I mean, you're seeing a sample. It's a larger sample, but it's still an incomplete random sample. What we're saying is that you can be very confident that the mean of that sample comes from a normal distribution with a mean equal to the population mean and a standard error equal to sigma over square root of n. That's all we're saying about the large sample size is that we know what the sampling distribution is. It doesn't mean it doesn't negate your desire to calculate a standard error or to do a hypothesis test. If you want to test a hypothesis that the mean from this sample is different from another sample or different from a population, you will still have to calculate the standard error and do these things.
So the thing is that if I have 500 samples or more, I can do my testings that assume that my sample follows a normal distribution.
Yes.
Since with 500, I can approximate very well to the central.
Exactly.
Nothing less, nothing more.
Exactly.
Okay.
So for large sample sizes, you can be very confident in assumptions based on the central limit theorem. So speaking of sample size, now what is going to happen to this null distribution, this null sampling distribution, as we increase sample size? Remember that when we changed the difference in means, nothing happened. When we changed alpha, nothing happened except that the size of the rejection, the position of the rejection regions changed, but this curve stayed the same. What happens when we change sample size? Let's say when we increase it. What did you say? Yes, it becomes narrower. If the central limit theorem holds, then it changes by 1 over the square root of n. Even if it's a t distribution and it's not central limit theorem, still it will become narrower. I think that take this up to 100. So this rescales so that it doesn't actually look narrower, but but it is. So because they're both narrower, this amount of probability of getting a statistic in the rejection region increases. So going up to n equals 99, power is now up to 0.997. Okay, and finally, if our standard deviation changes, let's say the standard deviation, I'll take this back. Standard deviation increases, what happens to the null and the alternative hypotheses, or to the sampling distributions under both null and alternative hypotheses? They become broader. Yeah, so the power will decrease as there is more overlap, down to a power of 0.228. So this is really the concept of power calculation, and it holds for different kinds of there are power calculations for proportions, for analysis of variance, for all sorts of different tests, but the principle is exactly the same, only the shape of these distribution changes.
I didn't see a change in shapes. I see that so it was going back.
Yeah, that's just this. I'll show you this.
And I expect to become like fat. And the smaller and the division become bigger.
It should. It's just a limitation of that tool.
Okay.
I'm going to give another. Okay, here's the one from the teaching demos package. A difference of 1, alpha equals 0.05, standard deviation of 1, a sample size of 10. Now I'm going to go up to n equals 20. And you see them actually getting narrower. Let's put a 40. How it should look. So you have both. As we increase sample size, the rejection region is moving to the left because the null distribution is getting narrower, and the alternative distribution is also getting narrower. So there's less and less overlap where you would fail to reject the null. Oops. Okay, I think we've covered all of this stuff, but here is just for your notes. Basic ideas, regardless of the test, is that your type 2 error will decrease, or your power increases the greater the difference between your null and your hypothesized alternative. The power increases also as the variability in the population, individual variability decreases, or as your sample size increases. And it stays. Your type 1 error doesn't change. That's just fixed. The customary thresholds for power when you're doing an estimation would be 80 or 90%. If you're planning an experiment, you usually don't want to bother unless you think there's an 80 or 90% chance of being able to reject your null hypothesis if the alternative is true. there are lots and lots of methods in R for calculating power. There are a bunch of them in this library power. There are other ones for different tests, like for survival analysis, and on and on. Monte Carlo simulation, which we'll talk about a bit in the next class, is a very useful way to do power analysis for people who know how to write programs like you that can help get around some of the complications of doing power analysis for different situations. And the idea behind doing a simulation of power is, you remember that when you do power analysis, you assume something for the alternative distribution. So you just program that actual alternative distribution, sampling distribution. Then you go ahead and perform your planned significance. First, you generate a sample from that alternative distribution. You do your null hypothesis significance test as you're planning to do, and then you just repeat that and see how frequently H0 is rejected. And that's a direct computational estimate of your power. And I use this in situations where the test is kind of complicated, and I don't want to try to figure out how to calculate it using theory or finding the right package to do it. You can just go ahead and empirically estimate power this way. Does this make sense? This is really just saying, okay, we showed those distributions about how you do it. Now you just actually go ahead and do it under your assumed true alternative hypothesis. So confidence intervals are in some ways closely related to hypothesis tests. And when they are possible, I think it's often fair to say that just reporting p-values, you're missing part of the picture, and you should also be calculating and probably reporting a confidence interval, for the main reason that your p-value says nothing about the so-called effect size, like the amount of differential expression, the amount of effectiveness of a drug at reducing cholesterol. It's just a probability of type 1 error. Whereas confidence intervals will tell you something about type 1 error while also giving you your estimated effect size and a confidence interval on it. The two cases where you're likely to calculate confidence intervals is where you have a normal sampling distribution or a t-sampling distribution. The approach is similar in either case. Your confidence interval is going to be centered on your sample mean, and then it will be plus or minus the critical value on your normal or your t-distribution times your standard error. Normal sampling distribution and you want a 95% confidence interval, all you have to do is multiply that standard error by 1.96. That gives you what you call the standard error, or sorry, your margin of error, and then by adding and subtracting your margin of error to your sample mean, you get a confidence interval. This comes up if you are looking at your output and you see a standard error, you can assume that it's normally distributed. It will, if it is called a standard error, also if it's called a walled test, that means that it's assumed to be normally distributed. So if you're looking in your output, you see something called a standard error, or you see something that's the output of a walled test, you can use this formula, 1.96 times that standard error, to get a margin of error and a confidence interval. Very, very handy. In the other situation, probably maybe less common for what things that you will do, but if you just have a sample and you want a confidence interval on its mean, you will likely use the t-distribution. There is an equivalence between confidence intervals and hypothesis testing that's fairly intuitive. That is, if you calculate your confidence interval and you find your null value somewhere in between the lower end and the upper end, then you fail to reject H0. But if that hypothesized value for the null distribution lies outside of your confidence interval, then you reject the null. But you do not do it by, this is a very common error, I think, by looking at overlaps between two confidence intervals. Just to draw what I mean, or here, you calculate, this is one confidence interval, this is another confidence interval calculated for a second sample. You would not say, you would not do your hypothesis test based on the fact that there is some overlap here. This is not evidence that you should not reject your null hypothesis. You might still, in fact, reject the null in this case.
If I have the two observations in the confidence interval, okay, and I can say that, okay, I can say that this value, okay, is statistically comparable with this one because they consider the overlap.
So the reason you don't do this is that this gives you a confidence interval for one mean, for the mean for one sample. And if this were a one sample test and our H0 were somewhere out here, we would reject the null hypothesis, and that's fine. But supposing that these tests or these two intervals under the null hypothesis, in order for them to have non-overlapping confidence intervals, you would have to have one of them be especially far to the left and the other one be especially far to the right. And it turns out that the probability of that is quite a bit less than 0.05 if these are two 95% confidence intervals.
But I cannot say that those two samples are statistically compatible, or actually I'm looking at the same thing.
Right. This can happen even if H0 should be rejected. And the correct way that you have to do this is by constructing a single confidence interval on the difference in means. Okay. We could try it in that we take two samples from populations with different means, and see how frequently we, or under the simplest situation, we take just a single population, we take 2 samples, and we reject the null if there's no overlap in their confidence intervals. And then alternatively, doing it the correct way, we do a 2-sample test and reject the null if the p-value is less than 0.05. And you'll find that doing it this way, you're going to reject the null much less than 5% of the time. Whereas when you do it correctly, you will reject it 5% of the time in a large number of simulations. Maybe doing it this way, you'll only reject it 0.5% of the time or something. It's something that I think almost everyone, when they first learn about the equivalency between confidence intervals and p-values, wants to do, which is why I kind of explicitly call it out now, because it's a case where your intuition is betraying you.
I've seen that many times.
I'm sure you have, yeah.
Personally started doing it as well.
Well,
Like
I think we could have time to actually do an example here, but can you believe that if both of those come from the same mean, so the null hypothesis is true, the probability of having one far enough over to the left and another one far enough over to the right that their confidence intervals do not overlap, is going to happen less than 5% of the time. So you can imagine most of the time, if, well, we'll have some examples coming up, some graphical examples.
If I'm evaluating the performance of a classifier over a repeated experiment, like the typical cross-validation,
yeah,
and I have 50 measurement for each feature step. So I'm trying to get out which is the subset of features that maximize my classification without taking all of them into account.
Right.
Okay. And I have that situation. And
yeah.
I cannot say that, for example, with 10, since the confidence interval overlaps with 50, which is the actual best, I can say that I can take 10 as my best because the confidences are overlap and I'm actually looking at the same thing. I cannot say that.
So I mean, you can always rank them by your point estimates, regardless of confidence intervals. But what you cannot do is say anything about a 0.05 type 1 error rate based on those confidence intervals.
And I also cannot state about equivalency.
Not about it. Well, I mean, you could never do that in the failure to reject the null is not evidence for the null. There could always be a difference that is too small for you to see, even if you're doing a correct hypothesis test. But the problem with doing this is you might fail to reject your null hypothesis of them being equivalent, even though there really is a difference between those two classifiers. You're being too stringent by requiring no overlap in the confidence intervals. Yeah. Yeah.
Okay.
It's not a test at the 0.05 level.
It's way harder.
It's way harder. That's right. It's way harder to have non-overlapping confidence intervals than it is to have a p-value less than 0.05.
Okay. Well, that's better.
Right.
In my case. Okay.
All right. So a quick true false here. which are these true? The 95% confidence interval contains 95% of the values in the population. Raise your hand if you think that's true. Raise your hand if you think it's false. Good, it's false. The 95% confidence interval will contain the population mean 19 times out of 20. Let's say this is not actually 20 times, but averaged over 1 million times, 19 out of 20. We've drawn 1 million samples. 19 times out of 20 of those, the 95% confidence interval will contain the true population mean. See your hand if you think that's true. Anyone else? That's true. That is the definition of a confidence interval, of a 95% confidence interval. How about this third one? The 95% confidence interval is 95% probable to contain the population mean. Yes or no?
I don't think that's true.
Yeah, they're right. It's a bit of a trick question. It turns out that, so there's another concept called what are they called? Not confidence intervals. They are plausible intervals, I think. The name is slipping my mind right now, but there is this third one is a Bayesian calculation. Credible interval, that's what it is called. And it turns out to be somewhat different from the 95% confidence interval. The second one gives our definition of a 95% confidence interval as you will calculate it. How about the fourth one? The 99% confidence will be wider or larger than the 95% confidence interval.
I guess the more is the 90, the less is the confidence. Should be.
What's that?
I mean, I guess that if 95 confidence interval is like this, 99 should be like this. It should be smaller.
What's your reasoning for that?
If I have like a point, the 95% confidence interval, I have like plus and minus some values. If I want to have 99 confidence interval, those plus and minus will be smaller.
Will be larger. To include more values. So you
Okay.
if you include the natural numbers.
Yeah, you're right. So you can think of it this way: the more confident you want to be in your interval, the bigger an interval you'd better have. If you give an interval from -infinity to infinity, you can be 100% confident that the true value lies in there. Whereas the smaller your mean is, the less confidence you can have in it. We should probably it's been 90 minutes, take a bit of a break, and then I went through an example from the book. We could go through some of that just to look at pictures, and then get started on the exercises. All right.
Ah, ecco, dalle 9 alle 10.
Okay, so just a few more. One example from the book that I think is pretty helpful for understanding confidence intervals and hypothesis testing. This is using this mice.pheno.csv data file, which we'll use some more later. And for this first example, it's a confidence interval for a single sample. So we've selected out female mice on the chow diet, and this is a somewhat not realistic example in that we're given the entire population here, and we know what the true population mean is, 23.89338. That is the mean weight in the population. And as Carlo said before, there's no standard error on this. There's no uncertainty. That is the actual mean of the population. Since in practice we don't have the whole population, we're going to take a sample from it of size n equals 30, use the sample function to take a sample of 30 of those, a simple random sample, and calculate its mean. In this particular case, we get a mean of 23.351 for this one sample. N equals 30, that's a large enough sample size for us to use the central limit theorem. So we'll assume that the means of samples follow a normal distribution with mean what we had for the population. So the means of the sampling and the population distributions are the same, and a standard deviation or a standard error of standard deviation divided by square root of n. So our estimate of this standard error turns out to be this 0.47. So these two things tell us what our sampling distribution should be. And this is an actual repeated random sampling. So we've repeated our experiment on 30 mice 3,000 times, something that we're not going to do in real life. So this just required 90,000 mice here to do these 3,000 experiments. But it confirms that our sampling distribution given by the histogram actually matches very well with what we expected from the central limit theorem. This red line being the mean of the population, and the blue curve being the normal distribution calculated from the central limit theorem. Matches really well. So our one sample had a mean somewhere about here. We see that it was actually closer than most samples to the population mean. It was closer than most samples that we would get as we repeat the experiment. So to construct the confidence interval from this single sample, we need the z critical value. There are these Q functions in R. That means quantile. The quantile for a normal distribution of the 0.97, the 0.975 quantile is 1.96. We can confirm that the probability between the 1.96 and minus 1.96 is 95% using the P norm stands for probability and the normal distribution. By the way, for all sorts of different distributions, they have equivalent probability and quantile generating functions to this. It's PT and QT for the T distribution. It's P binom and Q binom for the binomial distribution. They all have equivalents of these. So the 95% confidence interval is going to be from the mean, which is a z score of 0, up to plus or minus 1.96 standard errors. We can actually do it here. So using the standard error that we calculated, the 1.96, we add that and subtract it to the mean, and here is the confidence interval that we get. And note that when you do a t-test, it will give you not only a p-value, but a confidence interval. You'll notice a couple things in output of the t-test here. One is that the confidence interval is not quite the same. It goes to a bit of a lower value and up to a bit of a higher value. That makes sense, right? Because it's using a t distribution with its fatter tails, whereas we used a normal distribution. The difference is not too big because n equals 30, but there is still some difference there. We also notice a tiny p-value. Does anyone want to try to interpret that for us? We kind of got a p-value without going through all the steps of the hypothesis testing. But what would the first step have been if we were doing the actual hypothesis test here?
So one sample t-test.
Yeah, one sample t-test.
Mean equal to 0.
Yeah, so our null hypothesis here is that in the population, the mean mouse weight is 0 grams. So it's not a very meaningful null hypothesis. That's why this p-value of 2 times 10 to the minus 16 is not very meaningful. It also gives us this mean that's the same as what we calculated. Now let's repeat that 250 times. So we draw 250 samples, and each time we calculate not just the mean, but the confidence interval using this 1.96, the critical value of z, and plot them. So these are just lines going from the minimum to the maximum, and they're colored blue whenever that interval does not include the known true population value. We count these, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's about right. Right, because we expect 5% of them not to overlap with the true value. So 5% of 250 is 12 or 13. So these are pretty good confidence intervals. But we can use this to get back to this question about overlapping confidence intervals. So we have 5% of these not overlapping with the center line, but if you took any pair of those, there are not that many pairs where they actually don't overlap at all, right? Like here are 2 where there were fairly extreme samples that didn't include the population mean, but they still overlap. So that's because they both happen to be going over to the left together. So only in some of these very unlucky cases where you draw an especially small mean in one sample and an especially large mean in the other sample do you actually have non-overlapping confidence intervals. But it's quite rare. It's much less than 5% of the time. What if we went down to n equals 5? Count these, there's actually a lot more than 12. There's something more like 25 or 30 that do not include the true population mean now. You look surprised, Angela.
No.
No. Is anyone surprised? That's because the central limit theorem isn't such a good approximation anymore. We're assuming a normal sampling distribution, but it's not really normally distributed. It's actually t-distributed. And the t-distribution with 4 degrees of freedom has quite a bit wider tails than a normal distribution. If we redo it using the t-distribution with 4 degrees of freedom, we're back to having about the right number of confidence intervals that don't include the true mean. Just to see how big that difference is, the 97.5th quantile of the t-distribution with 4 degrees of freedom gives you a critical value of 2.77 compared to the 1.96. So this is how much bigger the margin of error is using the t-distribution than the normal distribution. So those 2.7 over 2, that's about 35% bigger The confidence intervals are about that much bigger using the t-distribution. And that is the correct one to use because we're estimating the standard deviation from the samples. If instead we calculated the standard error using our true population standard distribution, we would still use the normal distribution, even though it's a small sample size, right? That's not the case for most experiments that you do. You estimate standard deviation from your sample. So just to connect these two concepts, the confidence intervals and the p-values, let's take the mice who are on the chow diet and the high-fat diet. So we have two populations that have potentially different average weights. We're going to pull them out, make a control group from the chow diet and a treatment group on the high-fat diet. And now our null and alternative look like this. The null that those two population means are the same. Alternative is that they're different. We do a two-sample t-test just by giving the two vectors to the t-test function. We see this output. It says Welsh two-sample t-test. Welsh is a default in R. That means that it's not pooling the standard deviations. It's not assuming that the standard deviations of the two populations are the same. Got a p-value of 0.053 and a confidence interval of between -0.04 and 6. So you see that we have a single confidence interval, even though it's two means, and it's a confidence interval on the difference in those two means. So you have one mean that's 26.8, another one that's 23.8. So our point estimate on the difference of means would just be this minus this. It's about 3.02. That's the middle of the confidence interval. Then you see that your margin of error takes you below the no difference point of 0. So you would not reject the null based on the confidence interval or on the p-value. So does this make it clear the correct usage of a confidence interval for doing a hypothesis test? It's just a single confidence interval. It contains our hypothesized difference in mean under the null hypothesis, so we fail to reject H0. And if we go to a 90% confidence interval, so we're less confident, it means that the interval can be smaller. And you see that now with only 90% confidence, we are confident that the difference does not include 0. So the p-value is the same, but the confidence interval has shrunk as we went from 95 to 90%, or an alpha of 0.1 now. So just to wrap up, these normal sampling distributions are actually really common. They're called walled tests when they come up for individual coefficients in a multivariate regression. They're used in all kinds of multivariate analyses for multiple linear regression, generalized linear models, survival analysis. You often can assume a normal distribution for the coefficients of a multivariate model. Confidence intervals, they're more informative than p-values because they give you a direct estimate of your confidence of what you're interested in being in this range. And finally, high throughput analyses are often not any more complicated than this. It's just repeating it many times. If you're analyzing a whole transcriptome assay or a SNP array or a GWAS, you're just going to do quite a simple test and repeat it thousands of times along with multiple testing corrections. And with that, let's take a look at the lab. I'm going to shut off our Hangout.